Okay, so two things before I start. I realize I might not write big enough, so please, if at any point it becomes too small, stop me so that I can write bigger. And the second thing is I wrote here a reminder of the most important things from the last course. So, to recall, given a sequence X and the word W that appears in X, we defined the notion of left extensions, so the letters we can see to the left of W, right extensions, so the letter we can see to the right of W, and two-sided extensions, so the pairs of letters that can surround W. And based on this, we defined essentially two properties. The first we define is the neutrality, which is based on the multiplicity. So being neutral is saying that the number of two-sided extensions minus the number of left extensions minus the number of right extensions plus 1 is equal to 0. And the other property we define is dendricity. And this is based on the extension graph, because these three sets can be seen, well, the third set can be seen as a relation between the first two, so we can represent this as a bipartite graph. And when that graph is a tree, we say that W is dendric. Now, if you do a little research on dendricity, well, it was first defined in a series of papers, and studied also, in a series of papers by these authors. I think most of the papers were published in 2015. But at first it wasn't called dendricity. So originally, the definition here would be that W is a tree word, if its extension graph is a tree, right? But there was some conflict with our existing notions, so they decided to change it to dendricity for the Greek origin. Okay, so that was essentially what we did last time. We also did a drawing over there, but we won't really use that drawing today. And what I want to start to do today is try to give at least a little bit of motivation as to why we are looking at these graphs. Because it may not seem too natural at first. And for that, I need to talk about rosy graphs. Is it big enough? Yeah, okay. I'll try to keep it that way. Okay, so let me first give the definition, then we'll do an example. So the rosy graph of order n of X, of my sequence, is a graph. So it is a graph that we denote a gamma of n. Such that, well, the vertices of that graph are the elements of this. So these are the words of length n that appear in X. And this is a directed graph, and even a directed labeled graph. So I will have an edge from U to V labeled by A. So where U and V are words of length n. And A is a letter. Where? If there exists a letter B such that, and that's where I have to focus so as not to make any mistake, we have this equality, and this is also an element of my language. Okay, so this is the official definition. Well, official. There are different conventions for the naming of the edges, but this is the one I will take. But what does it mean? Well, it means that you will have an edge from U to V if at some point in your sequence you can take a window of length n. You see U, and if you slide that window by just one position, you will see V. Okay? So let's do an example. So I will take my favorite example, which is Fibonacci. So it's 0, 1, 0, 2, 0, 1, 0, and then again, leave, something like that, and so on. Okay. So what happens if I want to do the rosy graph of order 2? Well, for the vertices, I'll have to take the words of length 2 that appear. So there is probably a clever way of putting them, but I will do it kind of randomly and hope for the best. So I will have 1, 0, 1 there, 1, 0 there. Then maybe, maybe I'll put them in the middle. So 0, 1 there, 1, 0 there. Then 0, 0 above, and 0, 2 there, 2, 0 there. Yeah. I don't know if it's the best way, but we'll hope. Okay, so these are the vertices. Now, how do I find the edges? Well, I take a window of length 2, and I slide it slowly. So first I see 0, 1, then 1, 0. So that means I have this edge. And the label of that edge, actually, it's a redundant information because it's just the first letter of the starting vertex. So here will be 0. Okay, then I keep going. So 1, 0 becomes 0, 2. Okay, so far so good. Then 0, 2 becomes 2, 0. 2, 0, we go back to 0, 1. And we keep going, and we also have this, I guess, no, not that one, that one. So 1, 0, and then 0, 0, back to 0, 1. Okay. And we also have, well, there's this one. So we also have that one labeled by 1. Okay, and I can stop there because if you think about it, the edges then correspond to words of length 3. And I know how many words of length 3 I have in Fibonacci, and this should be fine. Okay, so far so good? Now, if you look at this graph, you can sort of summarize the information it contains by saying that essentially what you have is you have two vertices here, some path connecting them. So these two vertices will be these two. Right? And then there are 3 different ways of going back to the first vertex. Right? And these, as soon as you start in one of these 3 ways, then you don't have a choice until you go back to the first vertex. So essentially there are 3 different paths here. If you kind of summarize this. Well, it turns out that this is true if you take any order. So you start from Fibonacci, you take the graph, the rosy graph of order n for some n, then it will look like that. The only difference possible is that these 2 vertices are merged, but otherwise it will look like that. And actually, the reason Arnoux and Rosy started studying Arnoux-Rosy words is because their rosy graph looked like that, always. Okay, so this is a kind of motivation for Arnoux-Rosy sequences. Now, of course, what I want to motivate is dendricity more than Arnoux-Rosy. So, what is the link with dendricity? Well, let's keep going. Okay, assume now I forget that I'm working with Fibonacci. I don't know the word there. The only thing I know is that this is the rosy graph of order 2. And I'm trying to guess what would be the rosy graph of order 3. Okay? So assume we don't know. Too small, maybe? I'll try bigger. Okay, so we don't know who the sequence is. We only know it's rosy graph of order 2. Okay, so how can we find the rosy graph of order 3? Well, we already know that the vertices of the rosy graph of order 3 should be the words of length 3, right? And we know that in the rosy graph of order 2, the words of length 3 are somehow represented by the edges. So I already know what my words of length 3 will be. These are exactly the edges there. So this edge, for example, is 0, 0, then 1. So I have the word 0, 0, 1. Okay, then the edge on the right would be 1, 0, 0. And then here I have 0, 1, 0, and then 1, 0, 1. And then I'm trying to keep more or less the same relative places, but let's. Okay, are we good? Yeah. Okay, so these are my vertices. Just based on the edges I have there, I know what the words of length 3 are, so these are my vertices. Now, what are the edges I have between these vertices? Okay, well, let's first look at the top of the graph. So for example, here I know that if I take this edge, so in other words, if I see the word 1, 0, 0, then afterwards I don't really have a choice. I have to take that edge, so I have to see the word 0, 0, 1. So that means I know that I will have that edge, because this is the only possibility, so it has to happen. And then the label, I'm not going to write the labels because this would make the graph a bit too messy, but yeah. Okay, if we look at the bottom of the graph, same thing happened. If I take this edge, then afterwards I have to take that one, and then I have to take that one. So that means I have these two things. Okay, now the middle of the graph is a bit messier. So if I take that edge, afterwards I have 3 possibilities. Shouldn't it be 0 to 0 at the bottom? 0 to 0 at the bottom? Yeah, thank you. Thank you. Okay, so now if I take that edge, I have 3 different possibilities, and I don't know which ones are actual factors of length 4, so are actually edges in there. But what I do know is that before taking this top edge, the only possibility is that I had that horizontal edge. So by sort of reversing the reasoning, I also have this edge, because I have to come from somewhere and it's there, so and the only possibility is there, so I have to have that edge. And that also means I have these edges. Okay? And here on the left, it's even easier, because after this I have to take this, after this I have to take this. So up, I'll have these. Okay? So as you can see, using only the rosy graph of order 2, I was able to obtain the rosy graph of order 3 without knowing anything about my sequence behind it. Yeah? Okay, let's try again. Can we do the rosy graph of order 4? So once again, I will have, this one is 1, 0, 0, 1, then 0, 1, 0, 0, 0, 0, 1, 0. Then I can go there, so this would be 0, 1, 0, 2. I will have the symmetric there. Yeah.
A Rosy graph is basically encoding it's encoding an SFT approximation of it's encoding the forbidden subwords of length 2 or 3. And so what you're saying is that that there are no more subwords that I need to remove of length 3 if I want to remove those which I need to remove for order 2.
Yes, kind of. In this particular example, yes. If I know the forbidden words for this, then actually this also tells me the forbidden words for that.
You need more information to forbid words.
Yeah.
The Rosy graph will not be able to be constructed from the previous.
Yeah, exactly. And that is what we'll explain and we'll see here. Okay? So, in general, we cannot go from one to the other, from one Rosy graph to the following one without any extra information. But it sometimes happens that we can, and that's the case there. Okay, so let me keep doing this. So this one and that one. And then in the middle, I'm still missing some, so I will have 0, 1, 0, 1, and then 1, 0, 1, 0. Well, okay, I won't do the full graph, but let's try to see. So to obtain the vertices, no problem, that will always work. But now what about the edges? Okay, so if I take this one, I don't have any choice, so this is, I will have all of the corresponding edges, same for the bottom cycle. But in the middle, now we'll have a problem. Because for that edge, there are 3 different possibilities before. And similarly, for any incoming edge, there are 3 different possibilities after. And so this would mean that I don't know, okay, maybe I should have put the words a bit differently. So this one will go over there. And this one will go over there. And essentially, what I don't know is what happens in there. Okay? I don't know among all of these possibilities for these 3 incoming edges and these 3 outgoing edges, I don't know which ones are actually in my language and which ones are not. And if you look at what it means, well, having this edge, for example, means that 0, 1, 0 can be preceded by 0 and followed by 2 at the same time. So what you're missing is actually the extension graph yeah, something like that. So the information you're missing there is exactly the information of the extension graph of 0, 1, 0. This would tell you exactly which possibilities, which combination of incoming edges and outgoing edges are actually valid. Okay? So extension graph contain the information needed to understand the evolution of Rosy graph. And as you said, this Rosy graph of order 2 contains some information, contains some restriction on your sequence, but the bigger the order, the more information it will contain, the more restriction it will give you. And so what we really want to do is look at Rosy graph of large order. Yes?
So for Rosy words, you said that so they're defined by the fact that for each n, there's a unique word which has n extensions and a unique one which has one right and left.
Mm-hmm.
So each time these are different, you can do the previous argument as you said, because there's a unique way, and each time that it's the same one, that's the ambiguity.
Yeah, exactly. So the ambiguity comes only when you have words which are called bispecials, so words that have different possibilities on the left and different possibilities on the right. So for all the length of these words, you will have a problem in the Rosy graph. Well, you will need extra information. But all the other lengths, yeah, you don't need anything. Okay? Yeah. Okay, so this was some motivation for looking at extension graphs. It's because they appear in Rosy graphs. And Rosy graphs are a useful tool to kind of link combinatorial properties such as like factor complexity and stuff like that, and more dynamical properties, so acidic representations or, oops, will it stop? Yeah, kind of. Acidic representations or ergodic measures or geometrical interpretation or stuff like that. Okay, so now we start the second part of this course, and we'll talk about return words. Okay, so return words, I will define them in a moment, but these were really the first things that were studied for dendricity. Right? In the first paper on dendricity, results are about return words, let's say. Yeah?
So just a question about the example before. So, I mean, in the special case of Rosy words, I mean, there are still some hidden, like, what are the possible times at which you can have this bispecial word? Can it be arbitrarily large? Or?
Yeah, the gaps between bispecial words, yeah, will become longer and longer, I believe. But I don't know exactly the sequence of lengths, what properties had to satisfy.
Kind of like the Fantin approximation property or...
Yeah. Okay. Okay, so return words, what are they? Okay. Let me do some kind of example to give you the motivation for that. Okay, so. Okay, so take an interval exchange transformation. So I'll put my intervals in like that, and then I'll say that the small one gets there, that one gets there, something like that. Okay, and so remember, this is a dynamical system, so points will evolve according to the local translations. But imagine I don't know the full system. I'm not able to look at the full system, and the only thing I can look at is, I don't know, this window. Okay, so I can only see this window. I don't know what happens elsewhere. And so I have a point there, so I know it's there, and then it might spend some time outside and come back, and then spend some time outside and then come back, right? So it would go there, then somewhere over there, then there, I don't know. Maybe with my example it will spend a lot of time outside, but okay, oh no, now it's coming back. Okay. So this is a natural idea that you have some system, but maybe you're not able to look at the whole of it. So you only look at part of it, and you try to sort of see the induced version of your system when only looking at this small part. Okay. And there is a notion, dynamical notion of return time, which is the time it spends before coming back. Okay, and depending on the starting point, the return time might be different. But now, if we're in combinatorics on words, then we're not interested into how much time it spends outside, but maybe we're interested into what does it do when it's outside. Okay, so here would be, so if this is 0, 1, 2, here at the beginning it's in the orange part. Okay, it's in the orange part. And then it moves to the blue part, then to the white part, then back to the blue part, and then it's back in the orange part, right? And so if the time it spends outside is called return time, well, the sequence of what it does outside, kind of, is called the return word. So this is kind of the idea of return word. Let me now give the definition. So the return words to some W are the element of this set, which will denote ret of W. And so these are words, okay. Such that you start in something corresponding to W, you go back, and if you imagine you add an extra W, then you must start in W, right? You must be a valid path, you must actually correspond to something, so you must be in the language. But we're looking at first return words, right? So imagine here that we haven't come back in between. So we don't want to have something like that. Because this would mean that we missed a return time. We went too far. Okay? So let me do a more combinatorial example. So again, with my favorite word. Okay, I think it's still, yeah. So you can still see it on the top. But what would be the return words for 1? Well, you have to imagine, okay, maybe I'll copy the word because this would be more easy. Okay. So you have to imagine that you'd start at a point where what you see on the right is 1. And then you move forward until you again get to a point where what you see on the right is a 1. Okay, so we have here an example of a return word. So we start there and we end there. Okay. Now the next return word will be this one, and then we get the same one again, then we get 1, 0, and then we could potentially get more depending on what happens there, but actually I know that it's over. Okay? So in some sense, return words allow you to cut your sequence into blocks, and we'll come back to that idea tomorrow. I don't think I'll have the time today. Questions so far? No? Okay. So this is a combinatorial tool coming from the dynamical point of view of, well, symbolic dynamics. And one first thing we can notice is that I told you here that I know there's nothing more. I can close my set there. And why is that? Well, it's because result that we'll talk about now. So it's because I know exactly how many return words I should expect. So number of return words. Okay. So the first result on the number of return words is a theorem by Rion, which says the following: X is Sturmian if and only if the number of return words is always equal to 2. Right? So this is maybe not the most well-known characterization of Sturmian sequences, but this is an interesting one. And this, of course, since we're studying like generalization of Sturmian sequences, it's quite natural to then want to look at what is the number of return words in these generalizations. Okay, so if we try to count the number of return words, how can we proceed? Well, let's again do an example. And let's try to see why kind of there are only 3 return words in that case. Well, we know that any return words to 1 must start with the letter 1, right? And we'll actually exhaustively search all possibilities until we found all return words. Okay, so in Fibonacci, after 1, I always see a 0, so the only possibility to extend 1 is to have 1, 0. To extend it on the right is to go to 1, 0. Okay. Now after 1, 0, I have 3 different possibilities. I can either see another 0, I can see a 1, or I can see a 2. Okay. But you see that in the second case, I saw another occurrence of 1. Okay, so I know that this thing here is a return word to 1. And I also know that it's pointless to keep looking at extensions of this because I will have 2 occurrences of 1, and so I will not get any more return words. But the other 2 branches, I still have to keep going. So after 1, 0, 0, then the only possibility is to have a 1. And again, I see another occurrence of 1, so I know I can stop there, and that this will be a return word. Okay, so far we get the same return words as above, so that's always a good sign. And bottom one, after 1, 0, 2, we have to see a 0. We're not done yet, so we have to keep going, and this time we are done. And here, again, we have a return word. And now I exhaustively search all possibilities and manage to end all of my branches, so I know I don't have any more return words. Yes?
May I ask, so it seems that in the Fibonacci word case, the sequence of the return words is itself a Fibonacci sequence.
Yes. Yes, yes. Well, I mean, depends what return word you... Oh, maybe not all of them. Yeah, maybe. But yeah, it's a very... This is a very particular example. And it's also true for the Fibonacci one. But in general, this is not true for all our Neurosi sequences, that if you take return words, sequence of return words, you get the exact same sequence. That's not always true.
For our Neurosi, the number of return words is just the number of cycles in the graph.
Yeah, exactly.
You know there's only one way of going, and each cycle is giving you one return word.
Yeah, exactly. We'll talk about the link between Rosie graphs and return words in a minute. But yeah, this is another way of saying it. Yeah. Okay, but this exhaustive search, I can do it for any word, for any sequence. And so essentially the idea is that, well, the number of return words to some W is actually the number of branches I have at the end. And how many branches do I have? Well, at the beginning of my graph, of my kind of tree, I only have 1 branch. And then at each vertex, I have the possibility to split this branch into several parts. And so this is equal to 1 plus the splits for each vertex. So let me use some colors. So this would be the elements of my set S. And how many new branches do I create? Well, I have one incoming branch and it splits into this number of branches, so the new branches is this. Okay? Now, of course, this set S, you have to describe it. It's a bit complicated, and then you have to work on this sum and do some transformation and use combinatorics and so on. But you can show that actually the number of return word for W is equal to the number of letters in your sequence plus the sum over the V how would I say? W is not a factor H of V, and we sum the multiplicities this time. Okay. So the number of return words is somehow linked to the multiplicities of the words. Well, this is kind of natural because this is linked to the number of extensions, and we know multiplicities are related to number of extensions. Okay, but what can we do with that? Well, the first thing to notice is that if the multiplicities are 0, then the number of return words is simply the number of letters, right? And so we have this result by Balkova, Galantova, and Steiner that says that if your sequence is neutral, so if all of the multiplicities are equal to 0, then the number of return words is always equal to the number of letters. Yes? Oh. Can also do that, but yeah, bigger. Okay, yeah. I will rewrite that bigger. Okay, so okay? Now the converse is not true in general, because it's not because the sum of the multiplicities is 0 that all of the multiplicities have to be equal to 0, right? Some multiplicities can be negative. You have minus there, so they can be negative. And so you could sum multiplicities and obtain 0 sum, but not have 0 multiplicities. But there are cases where the converse is true. So now the converse is true in two cases. The first case is if all of the multiplicities have the same sign. So if, well, the only really interested case is when all of the multiplicities are positive or 0, non-negative then. Okay, so for all W. Because then a sum of non-negative numbers that is equal to 0 implies that all of them are equal to 0. Okay, so this is the first case where the converse is true. And then the second case, which is maybe a bit more difficult to see and I will not prove, is if your alphabet size is smaller than 3. Okay. But on larger alphabet, there are examples where the converse is false. So this one there. Okay. Any questions on that? No? Okay, one small remark I didn't do, but it's pretty obvious, is what would be the return word for the empty word with the definition we took. If you look at the definition, these are the words such that, well, W is empty, so such that U is non-empty, is in the language, and is not of length at least 2. So it's just A. Okay, so the return words to the empty words are just the letters. Okay, so this was for the number of return words, and we're pretty satisfied because, of course, if X is dendric, then it is neutral, so we already know the number of return words. Then we can go a bit further and look at the structure of return word. Okay. And why would it make sense to look at the structure of return words in the context of dendricity? Well, as we saw, dendricity is somehow related to nice property of Rosie graphs. They're not really easily describable, but nice property of Rosie graphs. And Rosie graphs are related to return words in the following way.
I'm sorry. So this is the question I meant to ask, because it says dendricity is related to Rosie graphs, but from the definition, it's clearly visible from the extension graph.
Yeah.
So my question is, what's the precise relation between the extension graph and the Rosie graph, and how can you, okay, you just said it's not clear how to read dendricity on the Rosie graph.
Well, the link between extension graph and Rosie graph is really the evolution I explained above. Extension graphs completely contain the information of the evolution of Rosie graphs. Okay. Now, actually the fact that this is a tree, it's not that clear what it would imply on Rosie graphs, but yeah, the link between extension graph and Rosie graph is really the evolution there. Okay, so the dendricity, or at least extension graphs, are related to Rosie graphs, and Rosie graphs are related to return words because every return word to some W labels a path from W to W in the correct Rosie graph. So in the Rosie graph of order the length of W, such that so that W is actually a vertex of that Rosie graph. Okay. So this is not too difficult to see, and you can check it on the example we have there. So you have the Rosie graph. Actually, oh no, we didn't. Well, the return words for 1 and 1, 0 are actually the same. So you can check there. But the converse is false. You have path from W to W that don't correspond to a return word and actually don't correspond to an element of your language, okay? Because Rosie graph contains some information and some forbidden patterns or forbidden sequences of patterns, but they don't contain all of the information, okay? And so the converse is not necessarily true, but still return words can kind of be seen in the Rosie graphs. And so it makes sense to believe that dendricity can somehow be related to the structure of return words, or at least some kind of structure on return words. Okay, but now I have to kind of explain what I want as a structure and what are the properties I will look at. And so for that, I will just do a little bit of free groups. Okay. So FA is this free group over A. And you should kind of see it as the words on the alphabet A and A minus 1. So for each letter, you also have an inverse letter. And you can do words on this larger alphabet up to, so you have some equivalence relation. So you need to simplify trivial factors. Okay. So if in your word 2 consecutive letters are inverse of one another, then you can just erase those. Okay. So this is this defines a group. It's a free group of the alphabet. And what I will really be interested in is what I will say. I will write like this. Maybe I should raise this one a little bit. Okay. So this is the subgroup of my free group generated by the elements of S. And so this is everything that you can obtain by concatenating elements of S or taking inverse of elements of S and concatenating them and so on and so forth. Okay. Okay, maybe just I'll do a quick example. Okay, if I look at, well, I could take that one. Okay, yeah, so 1, 0, 2, 0, 1, 0, 0, 1, 0. So if I look at the group generated by this, well, actually, I can see that if I take the inverse of that one and then concatenate with that one, I have simplifications. And so this is the same as the group generated by this. And then it's not too difficult to see that actually this is the whole free group over the alphabet 0, 1, 2. So this is the kind of thing I want to look at. Yeah, okay. So clearly, as every return word labels a path from W to W, then the group generated by return word is included in the group generated by all the labels of the path from W to W. So I will give a name to that group. So, I don't know, I will write it Rosie of W. So, is the subgroup generated by labels of path from W, from W to W. Okay. And so as a consequence of this observation, then right away I have that the group generated by return words is a subgroup of the group generated by path, by labels of path, right? But of course this, is it in the correct order? Yeah. Of course this inclusion or this subgroup relation doesn't allow me to really fully control what's in there, right? But we're lucky because the actual proposition is that there also exists a word such that I can surround my group generated by return words between two, I'm going a bit on the left to write bigger, so between two rosy groups, so the one of W, of course, and the one of UW on the other side. Okay. And this is a general result, well, assuming uniform recurrence. Okay, so now this is kind of controlled by rosy groups. And if all of my extension graphs are connected, well, this evolution of rosy graphs, and so also the evolution of rosy group, is sort of nice, so that but if every extension graph is connected, then yeah, okay. Should have put it the other way around. Okay. The other way around. I will say WU, so it works better. All of these rosy graphs, rosy groups are actually equal. Okay. So for those who know what this is essentially because you can do the reverse evolution of rosy graphs, so go from n plus 1 to n by Stalling foldings. And so okay. So then in that case, these two rosy groups are equal, so actually they also, this is an equality there, okay? And so this is a theorem.
By definition, the group generated by the return words to W is the rosy group, right?
No, because in the particular case of, well, okay.
What's the definition in this thing that rosy is a subgroup generated by a with a path from W to W? No, okay.
Not every path is a return word. So that's why this is really an inclusion. Okay. Now this is a theorem in the original paper on dendricity. And this is actually a two-part theorem. So if every extension graph is connected, then all of these groups generated by return words are actually equal to all of these rosy groups, and somehow you can show that they are equal to the whole free group. Okay. And now that means that in the dendric case, well, of course, the extension graphs are connected, so this is true. And we also have the property over there that the number of return words is exactly equal to the number of letters. So you have the return words are a generating set of the whole free group with the correct amount of elements, and so it is a basis. So if X is dendric, then the set of return words is a base of the whole free group for every W. Okay. And now we can do the same. We can ask, okay, well, is this a characterization? Are the converse also true? Well, for the first one, the converse is false. And the family of counterexample was provided by Hermann Goulet-Wallet. And for the second one, the converse is true. So this is the result we obtained. With and this is the converse. So if the set of return word is a basis of the free group for all W, then your sequence is dendric. Okay. And I will skip the proof and end there for today.
Thank you, Franz. Are there any questions?
I had one just to precise the definition of rosy W. The path that you are considering is in the rosy graph of length, the length of W. Okay.
Yeah, because
So it's not necessarily words that you can read in the infinite word X that you have.
no. So some of them won't be in the language. Yeah.
Any other questions?
So in the third column, in the proposition, if every extension of the graph is connected, then rosy WU. This is for the U that you chose in the just above, or it's for all U?
For any U and any W.
Okay.
Yeah.
Any more questions? If not, let's thank Franz once again.